Saxon Algebra 2, Lesson 99, Greetings students. Today we are going to talk about absolute value inequalities. We're going to be graphing them on just a basic number line, so that's fun. And we just want to briefly touch in on talk about absolute values and what that means. Remember that if we think of a number line with 0 in the middle, what an absolute value measures is the distance between that number and 0. So between 0 and positive 4, there are 4 units, right? 1, 2, 3, 4. But between negative 4 and 0, there are also 4 units. 1, 2, 3, 4. It doesn't matter which side of 0 we're on, we just measure the number of units from our number to 0. That's why absolute values are always positive. So if we're trying to find, for example, the absolute value of x, sorry, that's a little crowded, is less than 4, then what we want is all the numbers, all the positive numbers that are less than 4, so that would be 3, 2, 1, 0, but we can also have negative 3, negative 2, and negative 1, because the absolute value of those numbers will come out to be less than 4, right? 3, 2, 1. We don't have to repeat 0. A number like 5, the absolute value of 5, is that less than 4? No, that doesn't work. And therefore, negative 5 would also not work, because this would come out to be positive 5. Is positive 5 less than 4? No. So we could graph the solution, since it doesn't have the equal sign, we don't have to worry about the force. We would graph the solution, assuming it's integers in the domain, as between. Now, we don't want to have to go through this long process every time we graph an inequality. So we have a shorthand process for taking this and breaking it down into these two sets of numbers, and it looks like this. I always draw the arrows to remind myself that there are two versions of this. The first one looks exactly like it, only with the absolute value signs gone. We want the values for x that are less than 4, but they also have to be, and here comes the interesting part, we flip the sign, we flip from positive to negative. We also need the values of x that are greater than negative 4, and that's exactly what we've described here. Again, I chose integers as my domain. That was just my call. But that's what we've graphed up here, is values for x that are greater than negative 4, but also less than positive 4. So this process is going to be what we can use every time to graph these little puffs. So let's do example 99.1. Graph absolute value of x is less than or equal to 4, domain equals the integers. Okay, this is almost exactly like the example I chose. We draw the number line, we split this apart, we copy it first just taking off the absolute value signs, and then we do it again, flipping the sign. Notice I'm not changing whether it's equal to, right? That stays the same. We just literally flip it, and then we take the opposite of that number. Okay, and then we graph. This is almost exactly like my example. 1, 2, 3, 4, that's minus 4, that's 0, 1, 2, 3, 4, that's positive 4. We want to include 4 in our solution, but otherwise, that's what our picture looks like. And that's the right answer. Great. Let's make this harder, shall we? I know. Do we really have to make it harder? Yes, we do. Example 99.2. graph minus the absolute value of x plus 3 is greater than 0. Okay, so we're starting to complicate this by creating algebra that we're going to have to clean up in here. Domain equals the integers. Okay, so first we do the algebra just like before. We'll subtract the 3. Remember, subtracting does not flip. Adding or subtracting does not flip the inequality. Multiplying or dividing by a flips it. And by the inequality, I mean the sign. Okay? Sometimes people get confused and they think subtracting means we should flip that sign. No, that's fine. Absolute value of x is greater than minus 3. Okay, now we have to divide or multiply, however you want to think of it. I like to divide it by minus 1 on both sides because we have to get rid of this. Now we flip our sign. So now we get the absolute value of x is less than positive 3. And now we graph that. First we split it. X is less than 3. X is greater than negative 3. And we've got the integers 0, 1, 2, 3, 1, 2, 3. We do not want to include 3's in our solutions. We're graphing integers, so it's 2, 1, 0, 1, 2. And that's correct. Yay. Okay, so a little bit of algebra isn't going to kill us. Example 99.3. Graph minus looking at the book, and my problem isn't very straight here. This time our domain equals the reals, so that's a nice change. Draw some arrows. Again, we start with algebra. Subtract 2, we're trying to isolate that x, minus the absolute value of x is less than minus 4. And now we divide by minus 1. Again, subtracting doesn't flip it. Multiplying or dividing by a negative number is what flips it. So now we'll have absolute value of x greater than, this is positive 4. Okay? We split it into 2. I'm trying to conserve my space here at the bottom of the page. X is greater than 4, or x is less than negative 4. Okay, so this is a different kind of picture. This time, instead of coming together in the middle, we're going to be going out to the ends, aren't we? So here's negative 4, and here's positive 4. We want to circle and go greater than, and then here we want to circle and go less than. So that creates for us all the values that will make this original expression come true, and it will make either that or that. All of these values make this come true. All of these values make that come true. Okay. Now, in all of these 3 problems that we've done, once we got all the algebra, we had positive numbers in our inequalities. Right? Before we split it, excuse me, before we split the problem into 2 graphable inequalities, we had positive numbers. Let's look and see what happens if we get negative numbers when we finish our algebra. And I'll give you a hint. It's weird. Negative numbers do weird things. So we're going to look at 2 examples. We're almost to the end of this. We're getting close. Example 99.4. Oh, that's right. This one has 2 examples, and that's cheating. Absolute value of x is less than minus 2. Domain equals the reals. Okay, so what we're saying is we want to choose values for x so that their absolute value will be less than -2. But when we think about that, that doesn't make any sense because absolute values will be always positive, right? How can this value, if it's always be positive, ever be less than -2? It's impossible. So, we choose one of these, no solution. Just pretend that's not there. That's the way we express the impossibility of this. There's no way our always positive -2. That makes no sense. And so other weird situation, absolute value of x greater than -2, domain equals the reals. Again, an absolute value means the number will always be positive. So, what numbers can we put in here so that the absolute value of those numbers will be greater than -2? Anything. Any number we choose to go in here, negative or positive, will end up being positive, and that means it'll always be greater than -2. So in this situation, okay, this is my number line, and this is my solution. Every real number will be a solution to this inequality. So we draw the picture like so, expressing that everything is included. Okay, so what we see is that when we have negative numbers in our inequality, after we've cleaned it up and done the algebra, we'll get to that in the last example, we're going to have one or the other trick situation. So negative numbers at the end of our inequalities are always going to be either this situation or that situation, depending on whether they're less thans or greater than. So negative numbers present tricks. But here's an important reminder. We're going to graph minus x domain. This time we're going to say it's the integers. Doesn't matter. The domains just affect the way we draw the picture. They don't change at all the way we think about what's happening in the inequality. Okay, so we look at this and we go, aha, a negative number. But then that little voice in the back of our heads goes, no, it's not a question of whether it's a negative number at the beginning. It's after we do all the algebra and get a perfectly clean inequality. So we can't draw any conclusions yet. We have to do the algebra and see what we get. So I'm going to add 5 to both sides. And that gets me excited because I go, aha, now I have a positive number here. I'm fine. I'm not going to have a trick situation. But I'm still not done. So I better just divide both sides by -1. And that gives me, I'm going to draw a line there so it's clear, absolute value of x. Now because I divided by -1, I have to flip my sign. So it goes like that, and then this becomes -2. Okay, now I do have that weird situation with a negative number in my clean inequality, and I think about it for a second. I don't want to look and just read the answer. I want to figure it out. What values for x would give me a number less than -2? Well, this is always going to be positive. AP. I'm going to write that there. So this is impossible, so my solution here is null set, empty set, or no solution. I write all 3, just to remind you of what your options are. You don't need to write all 3, you can just pick one. What does John say? He says no solution, but those are fine too. Okay, so the thing with negative numbers is that once you get your inequality cleaned up with the algebra, if you still have a negative number, then you've got one or the other of the trick situations. So negative numbers always lead to tricks. Alright, that's the end of lesson 99. Congratulations, we are done with the double digits.
Less than 100 beckons.